So last time we started talking about Lyapunov exponents, right? And we introduced the definition of Lyapunov exponents, which is essentially if you follow a dynamics, the Lyapunov exponents determines the rate of growth of a small perturbation. Mathematically, it is defined as the limit of the 1 over t times the logarithm of the magnitude of the perturbation, right? So essentially, we define the matrix d phi with the index of t. That matrix is the linear operator that transforms the small perturbation at time equal to 0 into a small perturbation at time equal to t. So if the small perturbation decays, for example, if it's a stable system, right, then the matrix would diminish the initial perturbation into something smaller. If the system is unstable, then this matrix is going to amplify the initial perturbation into something bigger, right? So, for example, if it is an exponential decay or exponential amplification, then the magnitude of the amplified or decayed perturbation would be either exponentially large or exponentially small as a function of t, right? So in either case, when you take the magnitude and take the logarithm, that should be, as t goes to infinity, right? That logarithm should either be a positive linear function of t if it's an exponential growth, or negative linear function of t if it's an exponential decay. So if you take the logarithm, divide by t, right? That is the growth constant. If it's a positive number, that means the logarithm of the magnitude is a positive linear function of t, which means that the magnitude itself is an exponential growth. If the division of the logarithm by t is a negative constant, okay, that means the logarithm is a negative linear function of t, which means the magnitude is an exponential decaying function of t. So either way, as we take the limit of t goes to infinity, you get what's known as the Lyapunov exponent. A positive Lyapunov exponent means the perturbation with the initial perturbation of v would grow exponentially. A negative Lyapunov exponent means that if you seed the perturbation initially with v times an epsilon, right, then that perturbation would decay exponentially. In particular, what about a zero Lyapunov exponent? What does that mean? Yes, as we're going to see later in this class, a zero Lyapunov exponent is actually what we are going to see for a continuous time periodic system. What that means is that if you seed the initial perturbation, it will neither grow exponentially nor decay exponentially. Okay, well, what does that mean? That means the magnitude of the perturbation may still grow, it may still decay, but it just even if it grows, it doesn't grow exponentially. It may grow linearly or according to some polynomial, right? But not as fast as exponential. It may also decay, but it doesn't decay as fast as exponential. Or maybe it'll stay roughly the same order of magnitude, just sometimes grows, sometimes decays. So this is what we'll see for a periodic system and chaotic system. Okay, we're going to see that even for chaotic system, which is really defined by existence of a positive Lyapunov exponent, it's still, for continuous time chaotic systems, it still have 1 0 Lyapunov exponent. Remember, a system has more than 1 Lyapunov exponent, typically, right? So basically, depending on what the initial perturbation v is, just like eigenvalues, right? A matrix has more than 1 eigenvalue. A system has more than 1 Lyapunov exponent, depending on what v you initially seeded. Okay, so even for chaotic systems, we're going to see if you seed the initial perturbation v with something special, we are going to get a 0 Lyapunov exponent. We'll discuss that later. By the end of the last lecture, we also discussed that if we have a stable fixed point or unstable fixed point, the Lyapunov exponent of the dynamics around that fixed point is exactly the eigenvalues of the matrix that defines the dynamics around that fixed point. So in this sense, the Lyapunov exponent is just a generalization of a eigenvalue of a matrix. All right. Okay, so in this lecture, let's actually start computing the Lyapunov exponents for a periodic dynamical system. So we are going to start with a discrete time periodic dynamical system, and then we'll see what that looks like, and then we are also going to relate the Lyapunov exponent on a periodic system with, again, eigenvalues of a matrix. Okay, and then we'll move to continuous time dynamical systems and see how this notion generalizes to continuous time dynamics. Okay, so let's actually mathematically construct a discrete time dynamics that looks qualitatively like the Poincare map, the first return map on the Poincare section for the van der Pol oscillator. Okay, remember what that map looks like, right? If we have a x and f of x, let me actually now start from now on. Let's also call a discrete dynamical system phi of x, right? So that way, we have a consistent notation between a continuous time and then a discrete time dynamical system. So phi is going to be the map that maps a state from one time to another time. Except for a discrete dynamical system, phi with an index of 1, right? It maps over one time unit, is going to be a shorthand of just a phi. Okay, so let's make the map like that, right? So this is like the first return map of the van der Pol oscillator. If you remember, last time we actually plotted a bunch of trajectories of the van der Pol oscillator and looked at where the trajectory would return to the Poincare section of x equal to 0, right? So we are going to see if the trajectory started near the origin, it returns to the other side of the y-axis, right? If it starts positive, it just returns to the negative side. If it started negative, it returns to the positive side. With an amplified magnitude, that's when you start the trajectory near 0. But if you start a trajectory near here, near x equal to 2, right, you come back roughly at the same magnitude on the opposite side. While if you started very much away from the origin, then you come back and come to a magnitude actually closer to the origin, right? So let's actually, this is roughly what the map looks like. If you are near the origin, you get the, you get a value that's the negative of phi of x has the opposite sign of x, right? And with a larger magnitude. If you start away from the origin, then phi of x still have the opposite sign, but having a smaller value. All right, so let's actually mathematically construct such a map. Let's call it 2x divided by square root of a 1 plus x squared, and take a negative sign. All right, so this is a very common function to use as some kind of a logistic function, right? If you, there are all kinds of ways to construct functions that looks like this. This is one of the methods. You can also use a time h or some other exponential functions, but this is just one of the ways to do that. And let's actually, first of all, plot what the function looks like. So let's define a phi of x, just the return minus 2x divided by square root of 1 plus x squared. Okay, and if we say x is equal to length space of from -4 to 4, and let's plot x and the phi of x. I think all right, so this is the map that qualitatively resembles the first written map of the van der Waals oscillator, right? Okay, and now if we actually start with x, for example, close to the origin, 0.01, and we make let's say 200 iterations, and x dot append just to take the phi function operated on the last element of x. So basically x is going to be a trajectory, right? And now let's actually look at what x history looks like. We are going to see, maybe we just need 100 or 50. That might be enough to illustrate the trajectory. And let's actually plot x with a circle so that we see what each solution is like. All right. So this is what we observe. Initially, my x is very small, and it gets it oscillates around while the magnitude gets bigger and bigger until it reaches this limit cycle, right? So from there on, it goes positive to negative, and that basically is what we mean by a periodic cycle. Okay, so how do we compute the Lyapunov exponent on that? To compute the Lyapunov exponent, we just follow the definition, right? Look at how a small perturbation actually amplifies in this case. And we'll use what we learned last time of dealing with roundoff errors and truncation errors, right? So let's actually make an initial perturbation. So x, we are going to make x equal to, again, 0.01, but plus a very small imaginary number. Okay, so let's say 1e to the minus 100 j. All right. Okay. So then we are going to be basically doing the same thing, but then we're going to be focusing on the imaginary part, okay, of this number. So let me actually do it a little bit more rigorously, because so for every time, I'm going to say phi x is going to be phi operated on x minus 1 dot real. I want to compute the real axis. All right, and so then when I make the perturbation, d phi x is going to be phi operated on x, the previous x, including the real and the imaginary components. Okay, and then when I append the next solution, I want to append the phi of x plus d phi x dot imaginary part plus times 1j. So why am I doing this? The reason I'm doing this is I want to make sure that the real component, okay, is exactly the same as before. Okay, I don't want my perturbation in the real component to corrupt my imaginary component. All right, so basically what I'm doing is that I'm making sure that the real component is the same as in the previous example, right? And because there might be a small roundoff error due to the imaginary calculation flowing into the real component, right? That would, in this case, it doesn't matter. For a chaotic system, that small round of error might actually amplify and change my original trajectory, which is not what I want. All right. Okay. Any questions on why am I doing this?
So I have a question. When we just separate real part with imaginary part from imaginary part, it means that there is no perturbation on the real part. All perturbation and error increasing of error goes in the imaginary part, right? Will be in imaginary part or not?
Yeah. So what I'm all the perturbations are in the imaginary part, right?
Yeah. But we added some imaginary part as a perturbation.
Right.
Does this perturbation affect the real part, real component?
Yeah, exactly. That's what I want to avoid, right? So the imaginary part, the effect of the imaginary part on the real part should be roughly the square, the magnitude of the impact of imaginary to real part should be on the order of the square of the imaginary component, which should be so small that it doesn't affect the real part at all, right? But there might be real cases that even when that effect is small, it might change like the last bit of the real part. And that's what I want to avoid over here. Okay. So this way, I have made sure that the real part of this x is going to be exactly the same as if I just perform the purely real computation. Yes? How is this related to fractals?
Newton fractals, where basically we iterate with complex defined roots, and somehow we can just end up with mapping for perturbations and how the roots kind of converge.
I'm not familiar with that.
Okay,
Maybe we can discuss after the lecture.
Okay, sorry about that.
Yeah, Newton's fractals. Okay, I'll look that up. Yeah. All right. So now let's actually figure out. Let's make X an array and take the imaginary component. Okay. So dx would be equal to that, and let's actually plot what dx is like. So first of all, the magnitude of dx is roughly 10 to the minus 99, right? Or 10 to the minus 100, because that's how I perturbed it in the beginning. I think I might want to bring x. All right, so initially the value is 10 to the minus 100, and we can see that initially we have a transient growth of the perturbation, right? But the transient growth is actually during the part of the trajectory where we have not converged to the limit cycle yet. But after that transient growth, as the solution more or less reaches the limit cycle, the perturbation starts to decay, right? And ultimately it becomes something not even visible on the plot. Okay, so now let's actually, instead of plotting the magnitude, let's also, so what's the best way to visualize an exponential growth or exponential decay? Let's plot it in log scale, right? So let's say fig x is equal to subplots. Okay, so we are going to plot dx in linear scale first, and the semi-log y, because we see dx has positive and negative values, right? So we'll take the absolute value. And that's what we see here, right? So initially we have an exponential like growth, and then it turns down into a exponential decay, which is a linear slope on the semi-log plot. Okay, so what is this slope? I mean, the slope is actually the Lyapunov exponent, right? So because if you what exactly is the Lyapunov exponent? The Lyapunov exponent is take the magnitude at time t divided by the magnitude at time 0. Divided by time 0, and then take the logarithm, right? Which is equivalent of taking the logarithm of the magnitude here, subtract it from the logarithm of the initial magnitude, right? And then finally, we divided the logarithm by t, which means we are drawing a line between these and calculating the slope. Of course, right now, if you look at the initial perturbation being here and the final t being here, the slope is different from the slope you see at the end. But the Lyapunov exponent, by definition, is a limit of t goes to infinity, right? So as time goes on, as you continue the slope more and more, the slope between the initial point and the final point is going to approach this slope. Okay? So that is why actually we usually compute the Lyapunov exponent not exactly according to its strict definition, but we actually try to avoid this initial transient where it's going to introduce us some error. What we usually do is to take the initial v0 to be some point into the trajectory, right? Avoid, for example, the first 10 or 20 iterations and starts there. Use that v as the initial perturbation. Okay, so we'll show how much error we get on both cases. So if we start the computation of the Lyapunov exponent right from the beginning, what we are going to see is that lambda, actually in Python I can't use lambda because it's a reserved keyword, so I will just use lam, is equal to the absolute value of dx divided by the absolute value of dx0, right? And let me just use 1 to avoid taking, I mean actually just divide by absolute of dx0, and this whole thing is going to be taken with the logarithm and going to be divided by the a range of the length of dx, right? And let's plot what lambda is like. Yeah, so what we're going to see is that when t is small, it computed the lambda that's positive, right? That means we are still in the exponentially growing stage. But later on, it starts to converge to the Lyapunov exponent that's negative. That indicates that we should be seeing an exponential decay on the perturbation. But a much better idea is to start the computation not with a not at the beginning, but start from, let's say, the 20th iteration, and start from the 20th iteration and a range of length of dx minus 20. All right, so basically treat the initial 20 iterations as an initial transient, and then we can plot say length dx, actually just the length of lambda, and I'm going to plot the same, actually plus 20, so that I'm aligning the x-axis. So here I'm plotting the computed Lyapunov exponent if I use the 20th step dx as the initial v, right? Then we see that it's almost a constant, and it is actually the value which the blue line is converging towards. So if we run it for a lot longer, let's say 200, okay, and we then run these, we should see that the blue line approaches the orange line at a rate of 1 over the number of steps. Okay, so in this case, we should actually be able to analytically compute what the Lyapunov exponent is, right? Because at the end of the solution, if we actually print out, wait, what did I do? If I print out what is x at the last step, the real component should roughly be, should actually be exponentially accurate representation of where the fixed point is. I mean, not the fixed point, the limit cycle is, right? So basically, the dynamics would oscillate between positive and negative of this number, right? Okay, so if I can just differentiate this function at that number, right, for which I can do analytically, right? So if you take that function, phi prime of x should be, well, minus 2 divided by square root of 1 plus x squared, right? Then add with 2x divided by 1 plus x squared cubed, right? And then times yeah, basically the minus 1/2 power, so times 1/2, the sign, yeah, the sign is changed because of the minus 1/2 power. This becomes minus 3/2 power, right? And then times the derivative of the x squared, so times another 2x. And if you do the calculation, this is basically square root of 1 plus x squared cubed, and we have 1 plus x squared over here times minus 2, and on this part we have a cancellation, so we get 2 of x squared, okay? And with the cancellation of this and this, we get minus 2 divided by square root of 1 plus x squared cubed, right? So this is going to be the derivative. We can actually compute what the derivative is, and that actually gives us the analytical expression of the Lyapunov exponent. It is basically how much the magnitude of a small perturbation would amplify, right, while changing the sign, because this is negative, right? So if you take the absolute value of phi prime, that should actually be the Lyapunov exponent. All right, does it make sense why phi prime magnitude is Lyapunov exponent in this case? Okay, so if we take, yeah, so let me actually plot it over here. So if we take x0 is equal to x minus 1 dot real, and okay, and the phi prime is equal to actually 2 divided by 1 plus x0 squared to the power of 1.5, okay? And actually, it's the logarithm of this that should be the Lyapunov exponent. So let's plot, let's say 0 to 100, and log of phi prime. Log of prime. So basically, I'm plotting the analytical solution with a dotted line underneath. So we see that this is actually exactly what we computed, right? So the accuracy is actually very good. Okay, good. Any questions on the discrete dynamics?
So I missed the last part. What happened to the derivative?
Oh, So why the log of the derivative is the Lyapunov exponent? Is that the question?
Yes.
Okay, yeah. So this is because if you look at the map, right? If you look at the map, and draw a 45-degree line over here, the x would oscillate between this point and basically between this point and this point, right? So if you look at the small perturbation x, so x plus epsilon times v, so that's our perturbation, right? F of that should be equal to exactly, so let me just denote it in general. This is x as x1, this is x2, right? So because for a general periodic dynamics, it doesn't just oscillate between positive and negative of the same magnitude. So f of x1 plus epsilon times v1 is actually exactly equal to x2 plus actually this phi prime at x1 times epsilon times v1, right? Okay, and then if you apply this again to apply f again on the evaluated value v1, what you get is, because f of x2 is back at x1, it's periodic, going back and forth, right? This plus, I'm using the first order Taylor series expansion over here. You get, oh sorry, let me just this is phi, not f. Phi prime at x2 times phi prime at x1 times epsilon v1, right? So basically, after 2 iterations, where 2 is the period of this oscillation, I get back to x1. The x1 part is the same, but the perturbation part is amplified or diminished by a factor of phi prime at x2 times phi prime at x1. If I keep iterating, right, for every 2 iterations, the magnitude gets decayed or amplified by this amount. So after 2n iterations, okay, my v, let's say 2n divided by v, let's say 2n plus 1 divided by v1, right, is going to be phi prime x2, phi prime x1 to the power of n, right? Okay, so then the logarithm of the magnitude of, this is the magnitude, 2n plus 1 v1 divided by the number of iterations, which is 2n, would be equal to the square root of phi prime x2 times phi prime x1, right? And here, in our case, the map is symmetric, and phi prime of x1 is the same as phi prime of x2, right? Both are negative, so the product is positive. The square root of their product is just its absolute value. So that is why I'm saying the Lyapunov exponent is actually the absolute value. Also, sorry, not this. Actually, the logarithm of this. Right. So basically, the ratio is this to the nth power. If you take the log, we get n times the logarithm of this, right? And you divide by 2n, so we get half times the logarithm of this, which is the logarithm of the square root. All right. Okay, that's why in this particular case it's possible to actually compute the Lyapunov exponent exactly. And in general, if you have a periodic systems and you know the limit cycle itself, you can always follow the same formula, except for instead of if you have a period of 3, instead of a square root, you have a cube root, right? And instead of multiplying the 2 derivatives, you are multiplying 3 derivatives. And if you have a high dimensional system, instead of having multiplying the derivatives, you would be doing matrix multiplication of the Jacobians. All right. Okay, so this is for a discrete time dynamics. So now let's move to a continuous time dynamics, and we'll look at the van der Pol oscillator itself. Okay, so again, like the definition of the van der Pol oscillator, let's actually copy it from our previous. All right. And actually, in order to be able to do a complex integration, the ODE actually doesn't support complex integration. So we are going to be from scipy dot integrate import solve initial value problem. Okay, so that actually is a more modern interface that supports a complex state, and that actually requires the t to be defined in the beginning and you defined at the back. All right, so what we are going to be doing is basically do the same thing as before. So let's first compute the trajectory. Okay, so let's say u0 is equal to a revel of the x would be again equal to 0 n. So let's define x n to be, let's compute it just for a few trajectories. Okay, and the dot rand n minus 0.5, make it symmetric, and multiply by 6. So we'll say u is equal to solve initial value problem, and du dt and u0. Oh, actually, the t span has to be first. Again, let's solve it for 10 time units, and here we'll actually need to provide the t evaluate would be equal to length space of 0, 10, and I'll use 1001 time snapshots. Actually, solution is equal to this. It's going to be a structure that contains multiple things. U would be equal to solution dot y, I think. Let me actually print solution. Okay, solution, yeah, solution dot y is the solution, and so I think it has a different shape. Okay, so it's 6 by the number of time steps. So let's say u is going to be solution dot y dot ray shape 2 by n by the number of time step, right? Minus 1 means u is equal to the solution dot y dot ray shape. And let's just plot the solution to make sure we are solving the equation correctly. Transposing them so that we have the time dimension first. Okay, so that's again like the van der Pol oscillator solution, right? Okay, so now we are going to change it to feed it a random perturbation. So u0 is going to be u0 plus random dot rand n times 2 times 1e minus 100j. So that is our perturbation in the imaginary axis. So let's just make sure our real solution is still the same, right? So it's still, we get the real part of the solution being the same, but let's make x0 dot plot, and let's plot the magnitude of the perturbation. Okay, the magnitude of the perturbation would be u0, actually, So the second dimension is n, the number of solutions. So u square dot sum 0. So that's the taking basically the norm in the first dimension. That's the x and y dimension, right? And take the square root of that. Let's plot that. Subplots. Come on. Okay. Oh, I think I need to transpose that for that to work. Come on. Browser is not responsive anymore, so maybe. Oh, okay. All right. Got it back. Yeah, I think I plotted too many lines. Okay. Transpose. Okay. So here we see the evolution trajectory of the three trajectories, right? How the initial perturbation actually evolves for the blue, the orange, and the green trajectory. So it's pretty obvious that for the green trajectory, it started near the origin. So there is an transient amplification stage until it comes over to here. For the blue and orange solutions, there is no obvious like initial growth stage, and the magnitude just seems to be oscillating like that, right? So actually, let's integrate for a much longer time to better observe the long-term behavior of the growth. So instead of 10, let's actually integrate to 100 and that. Fixed size, let's make it 9 by 12. Okay. So this is again the trajectories, and this is how the magnitude of the small perturbation changes as a function of time. So what do we observe here?
It's oscillating between 2 points, which I guess is when it passes the fixed points.
Yeah, so basically we see the magnitude going up and down, right? But one second, why? Oh, actually, sorry, I should not be plotting the magnitude of u, but the imaginary part of the magnitude of u, right? That should be the that should be what I should focus on. So. Okay, so the magnitude is right, about 10 to the minus 100, right? And again, like for the blue and orange ones, they start relatively close to the origin, so they see initial growth in the magnitude. For the green one, it started more outside, closer to the existing limit cycle, so we don't see as much initial growth. But afterwards, what is the behavior of the magnitude of this perturbation? Do we see an obvious exponential growth or exponential decay? No, right? It seems that the magnitude of this oscillation is just there, right? It oscillates during each periodic limit cycle, it goes up and then goes down, and then at the next period it goes up again and down again. There is no obvious trend, exponential trend. So what does that mean in terms of the Lyapunov exponent? It is 0, right? So basically what we are observing here is that although the continuous periodic limit cycle is actually the continuous analog of our previous discrete time dynamics, right? We actually derived the discrete time dynamics in order such that it qualitatively resembles the Poincare map of this van der Waals oscillator, right? So there is a correspondence between them, but the Lyapunov exponent is different. The discrete time dynamics has a negative Lyapunov exponent, while the continuous time dynamics has a 0 Lyapunov exponent. So why does the continuous time dynamics have a 0 Lyapunov exponent? So this actually can be derived analytically. So let me first give you the intuition of why there is a 0 Lyapunov exponent. Okay, so let me imagine a perturbation. So let's imagine a limit cycle like that. Okay, so let me actually, instead of drawing it, let me just copy what this looks like. Actually, let me copy, I think, the previous plot where I skipped the initial transient. It's easier to do here. No. Yeah. Okay. Okay. This is too big. Second. Okay. So if I started a trajectory over here, imagine a perturbation in that direction, in the direction of the evolution. You can think about if we are computing the solution using a tiny time step. Just think about the perturbed state, right? We have u0, and we have a u at the time of t, and u1 as a time of t. And think of u1 just as u0 perturbed in the direction of the time evolution a little bit. So that u1 of t is almost exactly equal to u0 of t plus epsilon. Right? Then how would these two solutions evolve as you integrate in time? Well, if you started a u0 of if one starts with u1 of 0 equal to u0 of epsilon, right? So basically u1 is basically u0 after time shift. Then u1 of t would always be u0 of t plus epsilon, because they both satisfy exactly the same differential equation, right? So what does that mean in terms of the difference between u1 and u0 as time evolves? That means my u1 minus u0, well, at the same time t, is actually equal to, if you substitute the relationship, u0 of t plus epsilon minus u0 of t, right? Which is actually, if epsilon is infinitesimally small, this is actually equal to du 0 dt at u0 of t times epsilon, right? The derivative of u0 with respect to t. Make sense? So if I perturb the system so that it is a little bit ahead of in time, then the perturbed system would always stay that little bit in time ahead of the unperturbed system. Or you can also derive it in a slightly different way, right? So you can see if you have a differential equation du dt equal to f of u, right? Then here, this is exactly equal to f of u0t times epsilon, right? So if you always, if you have a differential equation like that, then if I make an initial perturbation v, if I make a perturbation, actually vt is equal to f of ut. So what is f of ut? F of ut is the direction of time evolution, right? Okay, then you can show that dv dt would be just a substitute df of u dt, and then if we use chain rule, right, what is df of ut dt? It is equal to df du times du dt. That's just the chain rule, right? And df du is, of course, the Jacobian of the system. Okay, and then du dt by the differential equation is just the df du dt is just the f of u. So this is by the differential equation. And what is f of u? Is just the vt. So this is basically df du times vt. That proves that the dv dt is equal to the Jacobian times vt, right? So vt actually satisfies the tangent equation. Well, what does that mean? That means if you start the system with a perturbation in the direction of f, that perturbation after a time evolution of t will still be f, but just evaluated at a different location on the trajectory. So as long as the system does not settle into a fixed point, right? If the system settles into a fixed point, then du dt will ultimately become 0. But if the system does not settle into a fixed point, then du dt would not go to 0, right? So it will not eventually decay. And also, as long as the trajectory doesn't blow up to infinity, right? If the trajectory stays within a compact domain in the phase space, then you can also show that the du dt will never actually go to infinity. So it will not decay, it will not grow. At the end of the day, there is definitely going to be a 0 Lyapunov exponent, right? As long as the trajectory doesn't go to a fixed point and doesn't go to infinity. That means we have the 0 Lyapunov exponent, not just for periodic mini-cycles, but also for chaotic systems that settles onto a strange attractor, right? I mean, the only difference is that for a periodic limit cycle, the 0 Lyapunov exponent ends up to be the largest Lyapunov exponent. And for a chaotic cycle, for a chaotic attractor, by definition, it has another Lyapunov exponent that is bigger than 0. All right, makes sense?
Definition, you mentioned that the perturbation should be in such a way that it goes in the direction.
Yes.
Otherwise, it doesn't, the Lyapunov won't be 0, right?
Yes, that's right. So let's actually let's actually look at our code, right? Look at our code we just wrote in computing this Lyapunov exponent, and let's not only plot the magnitude of this, let's also plot the direction of this to see if it truly aligns with the direction of the trajectory. So let's do that. So let's actually first of all plot the trajectory, plot the real components of the trajectory. Okay, let's then also plot the perturbations. Okay, so how do we plot the perturbations? We have u0 dot imaginary component, right? That's the perturbation in the x direction. And we also have the perturbation in the y direction. So what we want to plot is the following. So we want to plot u0 dot real minus u0 dot imaginary, and u0 dot real plus u0 dot imaginary. So basically we are drawing a line that goes from that basically shows the direction, right, of this perturbation. This is the y component, and let's actually ravel these. So this is the x and y. So let's plot this. And let's see. I want to skip every few solutions, so that otherwise I think it's going to be too dense. And yeah, that doesn't seem to be working. See what this does. Oh, I do need to transpose then. Okay. Wait, that's wrong. I think I raveled at the wrong location. So yes, I still want the end of the array to be okay. I think that's right. Okay, so basically we are plotting a bunch of lines, except for the perturbation is too small. So the perturbations are roughly 10 to the minus 100. So let's multiply 10 to the minus, let's see, 98 times the imaginary perturbation, so that we actually can see them. Okay, so still too small, I guess. 99. 99. The initial perturbation I think is 10 to the minus 100, right? Okay, so let's see. That should be visible. Okay, so instead of plotting every 10 iterations, I actually plotted the first 10 iterations. It should be this, right? So basically the begin, end, and interval should be what I should be aiming for. Okay, so now we should see the directions. All right, let me actually make a bigger figure and also capture the output so we don't Okay. So here we see how the three trajectories are evolving, both in the primal solution and in the direction of the perturbations. Right. So, for example, this one started with the perturbation in this direction. Of course, we amplified the magnitude of the perturbation by actually 2 times 10 to the 99 factors. Okay, because we are subtracted and added. The initial perturbation is actually a tiny fraction of what we are showing over here. But as time evolves, we can see that so this is basically what you can see is that as time evolves, the perturbation as the trajectory comes onto the limit cycle, the perturbation shown as the lines are becoming more and more tangential to the trajectory. So what does being tangential mean? Tangential means like the perturbation is actually in the direction of the time evolution, right? I don't know, maybe it's clearer if we integrate not over 100 time units, but actually over 10 time units. So that might make things a bit easier to show over here. Right, this is much clearer. So basically, no matter what initially you can see there is a transverse component of the perturbation. And as we evolve into the limit cycle, right, all the perturbations are becoming tangential to the trajectory, right? So that is a demonstration of not just the Lyapunov exponent being 0, but also the direction. What's known, we'll later talk about it, what's known as the covariant Lyapunov vector, the generalization of an eigenvector, is actually in the direction of what we have derived, right, is equal to f of ut or du dt. All right.
The question is that if we choose a different direction for our perturbation, the system will be different. Will have a different behavior or not?
Well, that's a great question. So we remember, like, we initially randomly chose the perturbations, right? So yeah, we randomly chose the perturbations in the imaginary direction. So your question is, if we chose a different random direction, would the behavior be different? The answer is no, right? The magnitude is going to be different, as we can see here. For different initial directions, this is not evolved for long enough yet, right? So if you evolve for long enough, all of them are going up and down in a periodic cycle, and the magnitude, as you can see, are drastically different. Just like an eigenvector can be scaled up and down, it's still the same eigenvector, right? But the direction is actually the same, right? It's as we evolve, the direction is always tangential to the trajectory. Okay, so why is that the case? We can decompose the initial perturbation into 2 directions. One direction is tangential to the trajectory in the beginning, right? The other direction is a direction that corresponds to the other Lyapunov exponent. So this system actually has 2 Lyapunov exponents. The 0 Lyapunov exponent is actually the largest one. There is another Lyapunov exponent that actually would really correspond to the Lyapunov exponent of like this discrete map, and that is a negative Lyapunov exponent. So we haven't talked about how do we compute that Lyapunov exponent or the direction associated with that exponent yet. We'll talk about that later. But if you're able to decompose the initial perturbation into the summation of these 2 directions, one along the trajectory, the other along the other Lyapunov covariant vector, then as you evolve, the component along the trajectory is neither going to grow significantly nor decay significantly, right? But the other component corresponding to a negative Lyapunov exponent is going to decay exponentially. What does that mean? That means as you evolve for long enough time, the other component is going to be less and less visible, at the end completely negligible, right? So the only component you are left is the direction along the evolution direction, along du dt. The argument is very analogous to like our eigenvalue computation, right? If you have a random initial vector, you can think of the random initial vector being a summation of multiple eigenvectors. As you keep evolving according to the say matrix, right? The eigenvector associated with the largest eigenvalue is going to be more and more dominant. At the end of the day, all the other components are going to be negligible, and only the eigenvector associated with the largest eigenvalue is going to be visible in the iterations. All right. So this is why, as we evolve the perturbation aligns with the trajectory. Okay. Any other questions?
On the direction remains for periodic system is the direction of trajectory.
Yes. Yeah. For chaotic system, we have exactly the same Lyapunov exponent equal to 0 and the covariant vector associated with f of u. But if you follow the same algorithm, right, of initializing a perturbation, you will not find this 0 direction. Right. Instead, you are going to find a direction associated with an even larger Lyapunov exponent, a positive Lyapunov exponent, right? That actually grows exponentially. So we will discuss that when we get to chaotic systems. But today, let's actually talk about something new. That is, how does a 0 Lyapunov exponent affect sensitivity analysis? So what do we mean by sensitivity analysis? Sensitivity analysis means we are analyzing the impact of a perturbation to the system. So instead of du dt equal to f of u, we now think about a du dt equal to f of u plus a perturbation. Okay, plus a perturbation. And one of the most interesting or a type of perturbation that has most applications is what's known as the parameter perturbation. So du dt equal to f of u and a parameter s. Okay, it's the same color. Okay, so for example, if you are just solving an ordinary differential equation, right? The S might be a parameter that controls how accurate you are integrating the ODE, right? For example, the tolerance parameter. So that's an example of S, right? Or it could be actually a parameter in the definition of the ODE. So the parameter perturbation is most often in the difference between a realistic experiment or observable system compared to a differential equation as a mathematical model, right? There is always parameter you cannot be exactly sure about in the real system. Okay, so the parameter perturbation, how does the parameter perturbation, the parameter S, affect the solution U, is the subject of what's known as a parametric sensitivity analysis. So parametric sensitivity analysis for a fixed point, for a stable fixed point, is almost trivial, right? So for a fixed point, let me just say what a fixed point, actually a stable fixed point. a stable fixed point is characterized by f of u and s would be equal to 0, right? So if you want to answer how does a small perturbation s affect the solution u, you would just linearize the system if the perturbation is small enough. So basically partial f partial u times delta u plus partial f partial s times delta s would be equal to 0, right? And your delta u would be just the Jacobian inverse times, there is a minus sign here, partial f partial s times delta s. So basically just by solving a matrix system, which is as easy, if it is not easier, compared to solving the nonlinear system, right? You can estimate how does the solution respond to a small change in the parameter. But starting from a periodic system, such analysis is no longer as trivial as for a fixed point. So let's look at what happens if you have a periodic system in the limit cycle. So you have a solution like this. And if by changing a parameter s to s plus delta s, my solution u goes from u plus delta u, let's see what is the governing equation for delta u. As we're going to see, the solution for delta u is very similar to the tangent equation that describes the small perturbation in the initial condition as we have been analyzing. But there is an additional term. Okay, so if you look at the time derivative of u plus delta u, it has two components, right? du dt plus d delta u dt. Okay, and that is of course equal to f of u plus delta u s plus delta s, right? That's by definition that the u plus delta u has to satisfy the differential equation governed by the same equation but with a perturbed parameter. And if you do a Taylor series expansion to this, right? This is equal to f of u and s, which cancels with this term, plus two parts. One part is the influence of delta u, that's df du, that's the Jacobian of the system, times delta u. There is a second part, df ds, times delta s. Now, because the first part cancels with each other, what we can derive is that d delta u dt is going to be equal to df du times delta u plus df ds times delta s. As I said, this equation is very similar to our tangent equation that governs the trajectory, perturbed trajectory, where the perturbation is the initial condition, right? Except for there is a second term. So this term is our new term. All right. So how does the periodic system, and particularly the zero Lyapunov exponent, going to affect the solution to this equation? Well, it affects the solution to this equation because there is a mode in this part of the equation that will never decay. Okay, and if the second term actually contributes to that mode that never decays, then there is an accumulation of the solution. The solution du would become larger and larger as time evolves. Okay, so intuitively, what does that mean? That means if the parameter s not only changes where the trajectory is, right? If it not only changes the location of the fixed of the limit cycle, but also changes the frequency or period of the limit cycle. Okay, what does that mean, right? So just imagine I have a parameter s that just changes the frequency without changing the location of the limit cycle. Then, after one period of time, right, the system with the increased frequency would be slightly ahead of the unperturbed system. Now, after 2 periods, the perturbed system, which goes faster, right, is now even further ahead. After 3 periods, it's even further ahead. So basically, how much ahead the perturbed system is now proportional to how many cycles I have gone through, right? So that's the effect of basically the delta U. The component of delta U in the direction of du dt would now be linear with respect to t. Okay, so the fact that without the source term, the system has a neutrally stable mode means with the source term, the solution would be linearly growing.
If we don't have the source term, the perturbation, it remains stable or not?
If we don't have this term, as we have seen here, right, this is the solution. This is the magnitude of the solution, right? And we have done this for 10 times longer. We see the solution never grows nor decays, right? So this is these lines is the magnitude of the solution without the source term. With the source term, it may linearly grow, and actually most likely it is going to grow linearly. Okay, so let's see this for the van der Pol oscillator. Okay, so here let's actually define the van der Pol oscillator in a slightly different way. So let's define the van der Pol oscillator actually with mu and a. So mu and a are the additional arguments of this function. Okay, so then in solve initial value problem, I think I need to provide an additional additional args. Args would be equal to basically the arguments for mu and a. Okay. Now I want to okay, so this is the initial perturbation, but when I make the arguments, I can also give an initial perturbation, for example, to mu, right? So I can add the 1 to the minus 100j to the parameter. So that basically gives the system not only an initial perturbation, but also a parameter perturbation in the imaginary axis. Okay, so if we do that and we plot, let's do it for 100 time units. So the solution looks like the same, but this is now the magnitude of the perturbation. Okay, so we no longer see an oscillation that doesn't grow on average in magnitude, but we see an oscillation that actually amplifies as time increases. Right? So this actually has important consequence in particularly in analyzing the sensitivity of a time average. For example, if you want to analyze what we usually call ergodic properties, right? So for example, what is the average magnitude of the oscillation? Or what is the percentage of the time the trajectory exceeds a certain value, right? Or what is the standard deviation of a certain quantity? What is the average of a certain quantity? They are all like statistical values, which can be represented as a time average or functions of different time averages, right? For example, the variance can be represented as the square of a time average minus the time average of a square. Actually, the other way. The variance can be represented as the average of a square minus the square of the average, right? So basically, different functions of averages. But when you take a time average, you can no longer the derivative of the long time average goes to infinity of 1 over t, not the derivative in time, but the derivative in the parameter, okay, of a certain j of u, time integration from 0 to t dt, is no longer equal to a time average of the derivative. So you basically can no longer change the derivative with the limit. Or in some sense, the derivative of a finite time average will no longer converge to the derivative of the infinite time average. What you are going to see is that because the solution to the tangent equation actually grows larger and larger, you are going to see that this limit, as t goes larger and larger, actually won't converge, right? This limit, as we're going to see in the next lecture, this limit actually doesn't exist at all. If you take the derivative of the finite time average, you're just going to see something that gets larger and larger. And of course, it'll be something different from the well-defined derivative of this limit. So we'll start the next lecture by explaining why parametric sensitivity analysis on the periodic limit cycle does not work the traditional way. And we'll discuss how do we use the ergodicity properties we have learned to fix this. All right. Okay, so I'll see you on Wednesday.